All right, so a polygon. So a polygon being a closed two-dimensional shape made of sides and vertices. Again, vertices is the plural of a vertex. When talking about a vertex, we've talked about it in a few different ways. The vertex for a polygon is when two rays or two segments connect, they intersect at a point. At that point is a vertex, and at the vertex is where we can find angles and angle measurements. So when we have a closed two-dimensional shape made of sides and vertices, it is a polygon. If we had a closed three-dimensional shape, then we're going to be working with polyhedrons. So the name changes from gon to hedron based off of what we're talking about. So an example of a polygon, that a star would be an example of a polygon. That is correct. I'm just going to keep it simple and go with a triangle. If you want to do a star, you're more than welcome to do so. Here's why I don't want to do a star. So I'm going to label all the vertices and the sides, and I don't want to do all 10 sides of a star. So A, B, and C would be my vertices. A is a vertex, B is a vertex, C is a vertex. This is a side, this is side. Yep, the sides and the points. So the first side, I have side segment AB because it stops and starts at A and at B. It's finite, or yeah, it's finite, meaning it stops. I also have a second side, which is going to be my side BC. And then lastly, I have my third side, which is, sure, CA or AC. It doesn't matter where it starts, where it stops. It's just that A and C are on this segment. So it's either CA or AC. So if you don't like the fact that we switch that around in your notes, you can write AC. So that's labeling a polygon. I can see that it's closed. It's not open at all. It has three vertices. It's made up of three sides. It's a polygon, also known as a triangle. So as long as it kind of meets that criteria, then we can say it's a polygon. Now for the first two words that may be new to you, convex and concave. So when working with convex polygons, that means that all the points are going to be, and they say outside the interior of the shape. So something like a triangle, none of the points are going into the interior of the triangle. They are staying on the outside. Sorry, I don't think sneezing is a symptom. Yeah. Oh, people are crazy. All right, so convex, all points and lines are not found in the interior. So some examples of convex polygons. Interior. You know what? I don't know why I'm freehanding this. An irregular concave one, yeah. All right, so when I take a look at this, something that would be on the interior. So I'm going to use my crayon, and if I just filled this in, all of this is in the interior. So I could add in some more sides or more vertices, and any of those points or lines went into that blue area. Then what would happen is that it would no longer be convex, it would be what we call concave. So whenever it goes in towards the interior of the shape, then it turns from convex to concave. Since I was able to draw this rectangle and none of the points are going into that interior, nothing's diving into it. It's almost like the if there's like a black hole in the middle of a shape and just started sucking the seas in, that's what would make it look concave. Whereas everything is kind of nice and calm, that would be convex. Convex is when all the points are on the outside. Concave would be like if you imagine a star on how it goes in, that would be concave. Both of these shapes are convex because none of them go into the shape at all. All right, so concave is when the points or sides are found inside the interior. So these would be two examples of concave polygons. They all are closed, but you'll notice with the first one, it was a rectangle. And then adding in two sides, one of the points, one of the vertices went into the interior and then back out. So because of this area right here, that's what makes the shape concave. Now with the star, you might want to argue that it's convex because the 5 points are all on the outside. But what would make it concave are going to be these points right here. And because we have those points, we've now formed new angles. Now we have angles right here and here, as well as up there. So this star has not only 10 sides, but it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 angles as well. Yes. So if so, the question was the first one, isn't it kind of convex since all the lines aren't inside? And if we imagine the original shape to being a quadrilateral rectangle, this side and that side is what's penetrating to the interior of the shape. So if you were to think of this as a rectangle, this and that are now going inside of my rectangle. And so it's because of that coming down, which makes it concave. So if you think like the top of the rectangle is caving in, and then that's what's causing it to become concave versus convex. Well, if there was a line on top, then it would go back to being completely convex because then this wouldn't exist anymore. Because if there was a line, then we'd go back to a rectangle. Yeah, so really, if it looks like a shape that you're used to seeing, most likely it's convex. It's the abstract stuff that you'd be like, what would you call this? That's most likely concave. And the answer to that question would be 1, 2, 3, 4, 5, 6. This is 7 sides. So this would be like a heptagon. And it's just a concave heptagon. Mm-hmm. So yeah, so we have concave and convex. Now, before I go into a couple other funky words, I do want to share with you something that I found online. And I just Googled names of polygons because I know a lot of names of polygons. I was curious, like, what else is out there? And I know that so many of them are not even going to be pronounceable. So I went on to the, what was that? Well, hedron would be three-dimensional. I don't know. That's a dodecahedron, or a dodecagon is a 12-sided shape. Mm-hmm. So if you were to Google it and then just look under Wikipedia, there's a bunch of stuff here, but I want to go right down to their names of their n-gons. And so they're kind of how many sides are there and what you would form. Now, they started off with a one-sided shape. So if you think about a polygon, that it has to have a starting point and a finishing point, but how could you do that with just one side? And that, by the way, is called a henogon or a monogon. Now, the ones that are in blue, but it has to be closed. So if it's just a straight line, it has to connect at some point. But lines don't bend. So how can you have a line that connects without it bending? But if you add heat and the line were to curve, it's no longer a line. So this is kind of the flat earther logic. And I'm going to get into that whole conversation. Well, I'm going to prove to you why they're right. Yeah. Well, we're about to ready to fight now. All right. So this is Wikipedia's version of a monogon. And you might look at that and say, that's a circle. But here's what's happening is that this would be equivalent to something like an equator around our Earth. An equator is a line. No matter where you go on the Earth, if you were to measure part of the equator, it's a line. Well, sure it is. If you get, and that's actually where calculus comes in, it's called local linearity. So if you were to take a curve and you were to take a small enough little snippet of it, it's going to be a straight line. It is. And in fact, and that's what calculus does, is calculus says that if you get infinitely close, between 2 points, it's a line. And so if you were to have the equator, which is an infinite number of little line segments, a bunch of little line segments should form a bigger line segment. Line segments don't bend. So how can the equator go around the Earth if it is a line? Therefore, the Earth must be flat because you can't go around the Earth and the equator is a straight line. Sure, there's obvious explanations, and I'm not saying flat earthers are right. I am no way a flat earther, but that's a mathematical reasoning as to why the Earth would be flat. If part of the equator is a line, and a bunch of those line segments make the equator, and the equator goes around the Earth, then it must be flat. But mathematically, you're right, it can't be round because lines don't curve. So therefore, the Earth must be flat because the equator is a line. Right, but that's just the mathematical argument that flat earthers could use, because if you know that part of the equator is a line and the equator next, then the entire equator must be a line. Lines don't bend. I don't know. I've never been to space, have you? On screens, on internet, it must be true. Anyway, a diagon would be two sides. So this would kind of be like the North Pole and the South Pole. Again, by the logic that longitude and latitude, those are also lines that go around our Earth. And it even says in the definition here that the construction is degenerate in a Euclidean plane. Now, anything that is a flat surface that does not bend is Euclidean. So that's what a Euclidean plane is. Euclid was a mathematician and a philosopher that he started creating geometry on a flat surface because he didn't know the Earth was round. I mean, this was back in the BC, like years and years ago. They may have had ideas, but they didn't have satellites back then. They didn't actually know what the Earth looked like. You just know that if this is level, then therefore it's flat. So why wouldn't you create shapes on a flat ground? because you can and you will. But the reason why this is degenerate in a Euclidean plane is because we're living on a spherical plane, like what the Earth actually is. If you were to take a straight line and put it on a spherical plane, it will bend around the plane. But technically, if you were to look at that plane straight on, it's flat. So that's where kind of geometry starts to manipulate, because if you look at the holistic thing, it bends. And if you look at a mirror that is bowed out like that, you can look at a shelf and it curves around the image. But the thing itself is a shelf and it is straight, but the image is curved. So it's just a way to kind of manipulate things. But that's a diagon. But then with the abstract, triangle, 3 sides, 3 angles, we all agree on that. You can see that that is a triangle. Next up is a quadrilateral. I really appreciated how they did this. They gave 6 different images for a quadrilateral. Now, a quadrilateral breaks down to being a 4-sided shape. So the quad being 4, lateral being lines, so 4 lines. Now, the first quadrilateral is the green one. That's a square. We're all comfortable with that. Below that's a rectangle. Below that is also a quadrilateral, but that would be a parallelogram. Both sides are parallel to other. Upper right-hand corner, you might look at that and think that that is a diamond. Fun fact, it's not a shape. It's a rhombus. I've been trying to teach my 4-year-old the word rhombus. He still calls it a diamond. I'm an idiot, right? No, we'll keep working on it. The blue one, it drives my wife crazy. She's an art teacher. She's like, no, it's a diamond. I'm like, no, it's not. It's a rhombus. Yeah, we get into awkward debates. I often just say that art is defined by math because math can explain all art, and then that sets her off. I know it's not true, but it's just fun to say. You can dissect anything with mathematics. So you can make the, yeah, that would be the Mona Lisa. Yep. The blue one there is a trapezoid. That just says that 2 sides have to be parallel. The other ones can be whatever they want. And that last one kind of looks like a starship. That would be a concave quadrilateral. So the other 5 shapes are all considered convex because you can see all the points kind of go out to their location. The red one's the only one that's concave because of the bottom part there, it kind of pinches in. 5-sided shape being a pentagon. And then we have a hexagon, a heptagon, or a septagon, depending on how you want to say that one. Octagon. We can have a entagon or a nonagon for a 9-sided, decagon. And then we keep going. That was the dodecagon we were mentioning earlier. And you can see that as we have more and more sides, this thing is starting to look like a circle. And so that's the logic behind, and the icosagon, why a circle has a local linearity, because if we were to zoom in enough, we would see a bunch of small line segments. Now, I was curious how high they went, and I was pretty impressed. They have, for a picture, as high as a megagon. And a megagon is a 1,000,000 sided polygon. Their best representation is a circle. So this megagon would also be convex because all the points are going out. About the shape that you originally, like what we were kind of originally talking about, where it's a one-sided. The monogon. It's kind of like how connect. Yeah, like how is that different from how many sides does that have? The megagon. This has 1,000,000. So how is the one-sided shape different from a 1,000,000 sided shape? So the question is, how is a 1,000,000 sided shape different than a one-sided shape if they both give the same appearance? The major difference would be like if I wanted to create a megagon. Think about having straws. Those are all straight, and you were to connect them. You could have everyone on Earth connect a straw, and you could technically connect around the Earth, and that could be, let's call it a megagon. Let's say it takes 1,000,000 straws to get around the Earth. You could create that. A monogon, we can't create, because if we were to take a line and have it go around the Earth, it would have to bend at some point. So one is impossible to create, but mathematically you can define it. Right. So it exists, but you can't do it. Whereas a megagon you could technically do. You could take a million toothpicks and then put them all in, and eventually you'd finish and you'd have a megagon. But it's physically impossible to create a monogon, but it's mathematically possible to define it. And that's like where math, like everyone says that math makes sense and math has like this concrete base, and but everything was made up. Everything in math was made up. Art, like combined colors, there's art, there's an argument behind creating orange, but like why is 2 plus 2 a thing? Our four symbols are only a few hundred years old, like addition, subtraction, multiplication, division. Those symbols we use are only a few hundred years old. And it's like we think that math has been around for the beginning of time, but it's just people just created it and said, look what I found, and then we just kept going with it, which is why math is so hard to understand, because it's just made up to begin with, and then you just make up problems that you don't need to solve just so you can solve them. It's insane. Why would anyone want, like, it's just but it's also fascinating. But yes, Stephen.
So, what if we had something that, what if we had like what if we took something that was long enough, we just laid it flat and
What if we had something like, what if we had like a PVC pipe that was long enough to go around the earth, sort of thing?
yeah.
Is because the earth is curved, the PVC pipe as a whole would eventually. Now, if you just took a small little segment and even closer than that, closer than that, closer than that, that will be straight if you were close enough. But as you get wider out, you'll begin to see that it curves. So it does have a local linearity to it. It's just not linear overall. And that's actually where Newton and Leibniz created calculus, because they realized that if there's a curve at some point, it is straight. And if it's straight, you can measure. And if you can measure it, you can predict. And so, a concept of derivatives and integrals, they eventually created all that stuff based off of the concept of measuring a curve and finding the limit, the distance between 2 points when they're infinitely close together. So what if we didn't have a megagon? What if we had something that had 10,000? So this would be a Chile Kismiriagon. That's 10 million size. I can't even say that word. And then they even did 100 million. And then they decided, well, what if we had one that had infinite signs? And that is the a periogon. So they actually named it. And if it has an infinite number of sides, it's one step below a circle. A circle doesn't have any sides, but if it did, it would be this shape. And I don't know how they came up with the names. Maybe they're just playing Boggle with the alphabet and just kind of got it. But
maybe they had a little tip.
Mhm.
Had like a random letter generator.
Yeah,
And like, let's hit this 15 times and make a word.
there you go.
Maybe they had a kid name it.
Yeah, they had 26 kids with a letter on their shirt, and they had, like, just hit them with like a water gun or something.
No, they had a kid name it. Hey kid,
Yeah. Yeah, and then spell it for us. So anyway, I just thought it was kind of cool to explore the different types of polygons out there. So in your homework, and we're not there yet, but just with your homework, I just asked you to create a polygon. So you are not restricted to triangles and quadrilaterals. You can have whatever you want. So anything that you think would be able to do it, if at all possible, to do so. You looking for Stephen?
I have to go to I have to do something.
All right, back to the notes. So we have polygons, we have concave and convex. What I'm going to lead into next are the regular versus irregular polygons. But before I can define what a regular polygon is, I have to go over two other words. The first word I want to talk about is an equilateral polygon. So we've already established a polygon is created of vertices and sides. But the new word is going to be that equilateral. And I mentioned it a few moments ago. And we can break up the word equilateral into two other words, two other bases. First is the equa part, meaning equal. Lateral, meaning sides. So a polygon that is equilateral means that all the sides are exactly the same. So it's going to become more uniform. So an equilateral polygon means all sides are equal. All sides of the polygon. The comment that just made is, why can't the government be like that? And technically, checks and balances, they tried, but where there's human nature, there is greed. And then the other fancy math term is equiangular polygon. Yeah, like asymptote. And these are, I do encourage you, especially when you're not around people, to be pronouncing equilateral, especially equiangular. It's kind of just a fun word to say, and if you're at home, you can say it all you want, but equiangular. So kind of like equilateral, equiangular starts with the equa part, which means that it's going to be equal. And then the angular, you can probably guess, is equal angles. So if a polygon were to be equiangular, that means that all the interior angles and the exterior, I guess for that matter, would have to be exactly the same. All right, so equilateral polygon, all sides of the polygon are equal. Equiangular polygon, all angles of the polygon are equal. Which brings me to a regular polygon. And that is a polygon that is both equiangular and equilateral. So if I were to have a regular polygon, that means that all sides are the same and all angles are the same. And I have just one more word, and that is the irregular polygon. That's got a nice, easy definition: when it's not regular. So that means that the angles can be different or the sides could be different. It's just that they're not all the same. So I'll just get you an example of what a regular polygon could look like. You putting those marks on the sides is a congruent mark. So that means that every side that has one tick mark is exactly the same. And then if I put a mark in the corner, that means that there is an angle measurement there. In this case, it's actually a right angle, so I could do the little square thing. But by me putting the arc mark in every single corner, I am claiming that all the angles are exact. What?
Looks like a sniper.
A little bit, yeah. So something that is irregular. Now the name is a little deceptive. Think irregular, that maybe it's something really, really weird. There's an irregular polygon. Now with this, a rectangle, it still has all the same angles, but this side is different than the other sides. So that is showing that this bottom and that top are the same side length, but the left and the right sides are also the same length, but different than the top and the bottom. And yes, it is equiangular, but it's not equiangular and equilateral. So if you want something that is irregular, that is an example of something that's irregular. If you want something that's regular, the square is something that is regular. Yes?
I'm also irregular in a positive way.
Comment made that they are irregular in a positive way. I suppose you could also be regular in a negative way too.
I know.
That's right.
Yeah, I get like
You can be any poly person you want to be.
really, I didn't know you squiggle.
All right, so let people finish writing this down, and then I did just want to show you one other thing, only because I want to try to use this software in class. It's called GeoGebra. Yes, it is. And so when people created GeoGebra, the reason why the name is what it is, it's a hybrid of the name geometry and algebra. And kind of like a cobra, yeah. And the idea is that you can use it to combine the two subjects. We are not going to go into great depth. What I think is the coolest thing about it is that you can draw shapes and it will measure it for you. So instead of finding the perimeter of a piece of paper that I'm giving you, you'll be able to measure it on the software and then calculate the perimeter, calculate the area, things like that. So if anything, it's going to help us, but it's just a way to visualize. So I want to show you a little diagram that was created on GeoGebra, and just so you have an idea of like what could be done on this software. So this is a little activity that I found on GeoGebra, that creating a regular triangle. So I want to create a regular triangle, meaning that all the angles and all the sides are the same. So in order to do that, you have to start off with 2 points, because you have to have one side that exists. Now, once you have one side, you now have one length measurement. And so if I were to extend that to a second point, and then back down to the third, you have now made a triangle. Now, what makes this triangle regular is that all 3 sides are congruent. Yeah, just like a windshield wiper. Now, they chose to do 2 tick marks on each side. It doesn't matter how many tick marks you use, just as long as all the sides share the same number of tick marks, then we know that this side is equal to this side is equal to that side. Next up, they're going to start with the angles. So we have this angle, and then it moves and rotates. It's the same angle, and then it goes up to this side. And we can see that this triangle is equilateral, because 1, 2, 3 sides are the same, and equiangular because all 3 angles are the same. So if you had this as your convex regular polygon, you would be correct. They also have one where we made a pentagon. So again, you have angle to angle to angle to angle, and finish it off. And then they have their sides. In this one, they chose to only do 1 tick mark, but again, all 5 sides are the same. So it doesn't matter how small or how big your shape is. Again, this would be a convex regular polygon. If this side was just a little bit smaller or a little bit bigger, in fact, there's just a little bit different. As long as it's still connected, if I just put one more tally mark in there, that's saying now that this is a different side length than the other 4. It's still a pentagon, but now it's an irregular pentagon. So that would be the difference between a regular convex polygon and an irregular convex polygon. It's just changing the length of one of the sides and not changing all the other ones. If you want to make this into being a concave, you could just take this vertex and bring it down into the interior so that it starts to cave in a little bit, and then we would be good with it being concave. All right, so back to our homework. I just want you to draw 4 pictures. The first, I want to be both regular and convex. It can be whatever shape you want, just make sure you have the marks of the sides and the angles. Next up, irregular and convex. Then irregular and concave, and regular and concave. Now, I am going to give you a hint because this was just, I was just thought it would be enjoyable. One of these is impossible to draw. Yeah, well, I let people suffer last block, and then people started to get annoyed. I'm like, okay, they didn't get as much joy as I wanted out of it. I will warn you that one of these 4 pictures cannot be drawn. So for your homework, you really only have 3 pictures to draw because one of them is impossible. But let's see if you can figure out which one it is. So I'm going to give you guys the rest of the time, which is a little over 20 minutes, 27 minutes, to get your homework done. So if you are remote, you can either be working on it, take a picture and send it to me. I'm going to mute myself so that I can have conversations here. If you have any questions, feel free to reach out to me. And the people that are in person, again, just showing me the pictures, and that will count as your homework. So if people at home get it, they're good, enjoy the rest of your day, get outside. It is beautiful out there. It's supposed to be in the high 60s. I really wish I could see something, but I suppose that would only depress me more if I was just seeing how beautiful it was outside. Or if you just want to stay inside, go for it, whatever. But anyway, enjoy the rest of your Wednesday regardless. And if you need anything, let me know.